Okay, so now we're going to talk about the correspondence between continuous and discrete Lagrangian mechanics. And so a big component of this is this idea of a exact discrete Lagrangian. Okay. Okay. So so let's denote this by LDE. Okay, and it depends on initial point Q0, final point Q1, and implicitly depends on a time step h. Okay, so this is defined to be the integral from 0 to h of the Lagrangian evaluated on some distinguished solution curve Q01. So I will write it down, just the fact that it depends on this action integral first, or short action integral just from 0 to h, and then tell you what Q01 has to satisfy, right? Where Q01, right, T is a solution of the Euler-Lagrange boundary value problem. Okay, and what that means basically is that Q01 at time 0 is Q0, right? This point Q0. Q01 at time h is Q1, this other point, and Q01 T satisfies the Euler-Lagrange equation. On time interval t between 0 and h. Okay, and one can show that this object exists, in particular the solution of this Lagrange boundary value problem exists, as long as the Lagrangian is non-degenerate, right? So this exists so long as L is non-degenerate. Which one way of thinking about it is that the Legendre transform which it induces is invertible, right? And H is sufficiently small. Okay. So there's an open. So if L is non-degenerate, then there's an open neighborhood about the about 0. For H, it's like such that this thing is sort of this object exists. Okay. All right. Anyhow, okay. So this is what we call the exact discrete Lagrangian. So let me prove some things about this, and in particular, how the exact discrete Lagrangian, in particular the discrete Legendre transforms associated with the exact discrete Lagrangian, how they're related to the continuous Legendre transforms. So let me state a lemma for you. So a regular Lagrangian, so this is one of these non-degenerate Lagrangians, L, and the corresponding exact discrete Lagrangian, let's call it LD, E, right, have Legendre transforms which are related in some way. Okay, and it's going to, the relationship is going to make use of this solution of the Lagrange boundary value problem. Okay, so it's going to be that FLD plus Q0 Q1 is going to be equal to FL applied to Q01 H Q01 dot H. Right, so that sort of makes sense. LD plus is in some sense a momentum at the right endpoint at the final time, and the claim is that that's going to be related to this momentum which we have here at the final time as well. And then FLD, well, F plus and F minus LD, I guess was the notation, right? Sorry, for the exact discrete Lagrangian, right? Okay, Q0, Q1, okay, H is equal to the continuous Legendre transform at the initial time, sorry, Q0, right? Okay, all right, so that's the main result here, all right? That's going to turn out to be important. All right, so let's, and then this is true for sufficiently small h, and then for Q0, Q1, which are close enough, right? Okay, and the closedness has more or less to do with the idea that this requires essentially something like a velocity being bounded, right? So if the velocity is bounded and the time step is fixed, then Q0 and Q1 can't be too far apart from each other. All right, anyway, so that's some intuition. So let's prove this result. Okay, so let's just prove one of them, and then the other one is sort of fairly analogous. Okay, so F minus LD, sorry, LD exact Q0 Q1 H, right? It's just defined to be the derivative respect to the first slot, right? So if you recall, FLD minus Q0 Q1, right, is something like Q0 minus D1 LD Q0 Q1. All right. So I'm going to sort of do a slight abuse of notation. I'm really just interested in the momentum part, right? The position part sort of clearly has the right behavior. Okay, so let's just look at the momentum part of it. Okay, so this is the minus D1 LD Q0 Q1 term. So that's just right, defined to be minus the partial derivative respect to Q0 of the exact discrete Lagrangian, right, which is L Q01 T. Okay, so Q01 Q01 dot T dt, all right? So that's equal to minus, and the integral from 0 to h. Okay, so I'm going to swap the derivative and the integral, okay? And then I'm going to apply the chain rule. So dl dq dot dq01 dq0 plus dl dq dot, right, dq01 dot dq0, right, dt, okay, and then I can do the usual thing. I can do an integration by parts, right, on this term, okay, so that's equal to minus the integral from 0 to h dl dq, okay, So if I do integration by parts, I take the derivative of this, I put it on here, and then I change the sign. I get minus d dt dl dq dot paired with the dq01 dq0. Okay. dt. But now I no longer have the property that this object vanishes at the endpoints, so I have a boundary term, right? So the boundary term is minus dl dq dot dq01 dq0 at h and 0. Okay, so I've done integration by parts here. All right, so the first thing to observe, of course, is that, let's see, where was I? Yes, so right. So the first observation, of course, is that Q01, it's like by virtue of the fact that it's a solution of the Lagrange boundary value problem, is a solution of the Lagrange equations. And so this thing here vanishes, right? Because, of course, that's nothing more than the Lagrange equation, which vanishes when evaluated on a solution of the Lagrange equation. So this comes from the fact that Q01 is a solution of the Lagrange equations, right? Okay, and then we have to deal with the second terms. Okay, all right. Okay, so dq01 dq0 at time 0, okay, is just the identity map. Okay, because q01 at time 0 is, of course, just q at time 0. And so if you differentiate with respect to q0, it's like nothing happens, right? That's not very exciting. Okay. And dq01, dq0 at time, the final time is 0, because q01, it's like satisfies the boundary conditions, right, which are prescribed. So in particular, q01 at h is always q1, and it's independent of q0, so it has to be 0. Okay, so if you substitute this into this term here, then what you get is that f minus LD exact q0 q1, right? This term here vanishes, so you're just left with the boundary terms. This is 0 at the h, and so the only thing which is left over is the one at time 0, which is, of course, where was I? Okay, which is, of course, okay, so minus, and there's a minus here because it's the other endpoint, right? So you normally evaluate this at h minus evaluating this at 0, but it's a minus, so you're just left with that thing evaluated at time 0, which is just dl dq dot, right? And then it's evaluated at the solution of the Lagrange equations, sorry, of the Lagrange boundary value problem at time 0, which is q01 at 0, q01 dot at 0. Okay, so that's exactly what we wanted to prove. We proved this, and then it's like the other statement is sort of analogous to this. Okay. All right. Okay. So let's now try to. So I'm just going to keep this up here for now. It's like, and I'm going to erase this, and I'm going to draw a commutative diagram. It's like which basically sort of gives you an idea of what this is actually saying. Okay. So what happens is that statement, these two statements, are equivalent to the following. All right, so you have Q0 and Q1, okay? And you can map them under the plus and minus discrete Legendre transforms with respect to the exact discrete Lagrangian. So this is F minus LDE, okay? And then F plus LDE, okay? And we're saying that this is Q0, P0, and Q1, P1. But more importantly, right, this is related by the continuous Legendre transforms, okay? So this is related by FL and FL to the Q0 and Q0 dot, okay? And Q1 and Q1 dot. And then this here is the exact flow of the Lagrange equation. Okay, so let's call that FHL. Okay, so this is the diagram we have, and so I can erase this. Then if you recall, you know, the discrete Legendre transforms also allow you to define both this discrete Lagrangian map and a discrete Hamiltonian map. Okay, so let's just fill this in, right? So you have a Q1, Q2, F minus LDE, F plus LDE, all right? Q2, P2, all right? And so I can fill this in. And as you might expect, I can fill this piece in here as well. All right, this is the discrete Hamiltonian map, F tilde LDE, and then this is what I called FLDE, right, which is the discrete Lagrangian map, and F tilde LDE. Okay. And of course, you know that if you have the all-Lagrange flow with a regular Lagrangian, then this is conjugate to the exact Hamiltonian flow by the Legendre transform. Okay, so you know that this diagram, right, also means that this has to be equal to the exact time h flow of the Hamiltonian, FH. Okay. So this then says basically that the discrete Hamiltonian map generated by the exact discrete Lagrangian, it's exactly the time h flow map of the Hamiltonian of Hamilton's equations. So this implies that the discrete Hamiltonian map F tilde LDE generated by the exact discrete Hamiltonian the exact discrete Lagrangian LDE, right, coincides with the exact time h flow of Hamilton's equations. Okay, so put another way, if you have, again, this regular Lagrangian, then there's this nice correspondence. It's like between continuous Lagrangian Hamiltonian mechanics and discrete Lagrangian mechanics if you use this exact discrete Lagrangian LDE, which is obtained by evaluating the action integral over a short time interval on the solution of the Euler-Lagrange boundary value problem. So let me stop here.